Hi, Chindaga.
Hi, Bobby.
So, what shall we do today?
I think maybe
We'll continue with the resistive sensors.
continue where we left off, I think.
Yeah. So, I remember we had this expression, let's say Rx, because resistance was changing. Let's put Rx equal to rho L by A. And then what we said is we will make use of this L somehow.
The length?
Length.
Yes.
And we had a structure like a coil, not coil, some wire.
Why? Wound around the bobbin.
Yeah, which has some resistance.
Yes.
It wound on a bobbin, and then there was a wiper,
Yes.
which we moved with respect to the displacement.
Yes.
After that, we also had some improved versions and so on.
Yes. Correct.
But one thing, we are still waiting to make use of the other parameters. I mean, I have area, so, and the resistivity rho.
Yes.
So, what about those guys?
So,
Why not use those also?
So you're saying now we can not just use L,
Yeah.
but also the cross-section area
Yeah, I'm getting greedy.
and the resistivity.
Yeah. So,
But then if all of them are changing,
hmm,
wouldn't that be a problem? Because we will not know what is changing.
it could be a problem.
Yeah.
But for some materials, for certain dimensional change, I may have more change in resistivity.
Okay.
And for the same amount of, dimensional change that I have, I would say, let's say, some delta Rx with respect to change in A or change in L or change in rho, which one contributes more?
Okay.
That depends on the material, shape, etc.
Okay. Is that something we are going to look at today?
We can probably look at that.
Yeah.
And as you said, if you want to look at maybe L alone, even L, here we did not actually change the dimension. You have a wiper that essentially changed the length or active length.
Yes. Yes.
Somehow,
Indirectly.
So this time maybe we could really change the L and see how it will contribute.
Right. So would it be fair to say that you're changing now the actual dimensions of
So I'm going to
sensing
take a piece of resistive element and pull or push,
Okay.
change the physical dimensions and see how that will contribute to this change in Rx.
Okay. Now, Bobby, I remember you saying that it's not good to change with the sensing element or modify it.
Yeah. So sensing element modification, it's all relative.
Right.
I mean, the way I showed, it looks like I'm going to expand in centimeters.
But we are talking about small changes.
It may be some micrometers.
Yes. The naked eye cannot really see.
Yes.
Right. just I just want to make sure,
Yes.
Unless we just keep pulling things and
Correct. Yeah. So that kind of change can also happen if something goes wrong, probably. We will see.
Okay.
So what is this? So I have some nice steel structure.
Yeah. It's like a cylinder.
Yeah. It's a cylinder.
But
What I see is some structure here which is pasted on it,
Yes.
and then some nice, beautiful wiring.
Yes. Quite a few wires there.
Yeah. What is this?
And this is pasted around or on the face of
This
the
is pasted like a skin. It is pasted on
the structure.
structure.
On the cell structure.
Yeah.
No, I see a line.
Yeah.
I'm not sure what this
Then we will try to understand more.
Okay.
Essentially, I wanted to see what it is, how it behaves, how this can be made use of, etc. But at the moment, I don't know what it is. So we were talking about the dimensional change.
Yes.
So consider I have a cylinder like shown here.
Okay.
It has got some, what shall we say, if I take the cross section, it will have some diameter like this.
Yes.
Or cross sectional view like this. It will be circular. My drawing is somewhat elliptical.
Okay. But yeah,
Yeah.
if you look at
Yeah.
from the side.
So that has got diameter D.
Okay.
So let's say this is hooked at the top. I mean, it is attached at the top.
Yes.
And then, like I explained earlier, I am pulling this down.
Okay. You're pulling it.
Yes.
Okay.
I'm pulling this down. So see, there is a force F applied. And then this piece of metal, I'm pulling down.
Okay. So this structure here that you've shown, it's like a diving springboard where it's fixed, and then does it move up and down, or is it totally fixed?
It's not like that.
It's a solid structure.
Let's say I have a structure like this.
Okay.
This is held at the top. Then I am just pulling down.
Okay. Okay. And this does not move this way.
No. Okay. No. It's only this way.
This way. Okay.
So when I do that, definitely depending on the force I applied, it will get elongated.
Yes.
So that is what this dotted shape shows.
Right. You're going to change the length.
Yeah.
Increase the
And
length.
the volume has not changed.
Yes.
So that means there is a delta L, means an increase in the length, and then there will be a decrease in the diameter.
Yes. If you pull hard enough, I guess.
Correct.
Yes.
Correct. And as I mentioned, this change could be some micrometer.
Yeah.
It may not be large.
Right.
Depending on the force you apply and so on. So this means now consider this is a resistive element. Okay. This cylinder, if it's made of, let's say, some material called nickel, for example.
Okay.
It's a resistive material.
Yes.
And if I try to measure the resistance of that, there will be a change now.
Yes, because now you change the length.
Yes.
And the diameter.
Yes.
Yes.
So this delta R, change in the resistance, will be contributed by change in the length,
Yes.
change in the cross-section area,
Yes.
and even when it undergoes dimensional change, it may get compressed or elongated and so on. So the resistivity may also change.
Yes.
So it will be a function of all this. Function of area, length, and resistivity.
Yes.
So if I want to mathematically somehow represent, I may have to use some partial differential equation.
Yes.
So this delta R could be, it will come from, let's say, dou R by dou L
Yes.
into delta L.
Delta
Then there is dou R by
to A.
dou A into delta A.
Yes.
Then again dou R by dou rho
Delta rho.
into delta.
Yes.
So it could come from all this.
Yes.
Now, as you said, one of this may be more sensitive.
Yes.
That we will see.
We don't know the dominant.
Yes. It depends on the material and so on. Right. And resistance, earlier we said it is rho L. Or what? Sorry. We said somehow it doesn't like writing in that portion.
Maybe it's too close to the top.
Yeah. So we'll write here R is equal to rho L by A. So maybe we'll just differentiate and introduce and see. So this will be rho by A into delta L. This will be, because A is in the denominator,
Yes.
this will become minus rho L by A square
Yes.
delta A plus L by A
Del rho.
into del rho. See, before doing this, I had some chain resistance. And then there is a delta L.
Yes.
So I would like to see the relative change. So I would like to probably get delta R by R.
Right. So dual by R.
Yeah.
Your original resistance. Yes.
With respect to something, I would.
Yes.
So maybe we will rewrite this. So suppose if I, let's say if I multiply it and divide by L, then I get rho L by A, which is R.
Yes.
So this will be R into delta L by L. Similarly here, I don't have to do anything, I think. Rho L by A is already there. I can move one A here.
Yes.
Similarly here, I will multiply with rho and divide with rho. So if I do that, I get R into delta N by L minus one more times R into delta A by A plus R into
Delta rho
by rho. So now I can comfortably write delta R by R, which is a relative change in resistance, equal to
delta L over L minus delta A over A plus delta rho over rho. So that's your change in resistance.
That's our, now it's a relative change in resistance.
Yes.
Because it's with respect to the R,
Yes.
which was there originally.
Yes.
Or before the dimension change. So as we expected, all these terms are contributing. One difference we see is when length increases, of course, area goes in the other way.
Yes.
So that is seen in the
Yes.
polarity there.
Yes.
Hey, why are we doing this? So we wanted to see whether dimensional change can be
Translated
into change in resistance,
yes,
and somehow make use of.
Yes.
I look distressed today. So if some material undergoes stress, it will be seen as a strain in the.
Yes, there is some deformation.
Yes. So strain is nothing but a dimensional change. For example, delta L by L.
So you're here applying a stress, which is a force.
Yeah.
Right? And then you see a strain.
Yes. And that strain is seen in the resistance change.
Yes.
Right.
Yes.
Now, if my objective is to measure the stress, or I'm measuring strain, from there I get the stress.
Yes.
Let's say objective is to measure the strain.
Yeah.
If so, should I, how will I use this? In the sense, see, I showed a structure before, a big one.
Mm-hmm.
Right? This is carrying some load.
Yes.
Assume.
Mm-hmm.
Or, one side it's a motor and other side probably it's a load which is rotating.
Okay.
Or one side is fixed and other side is maybe just holding some load.
Okay.
All these are possible.
Okay.
So, or as we explained now, it may be, it's like a ceiling fan. Top is fixed, it's hanging and some weight is carried by this.
Okay.
So there is some small dimensions which may not be obviously seen for the eyes, as I said. So, will I go and measure the resistance of that big structure, or will I attach something to that for which I know what material it is and where I can measure the resistance?
I would go for the second option.
Because if something is in our control, we would like to, we are more happy.
This is true. Yeah.
So, because this structure may be made by someone, I may not have the data.
Mm-hmm.
So, also it may not be that easy to measure the resistance of a big structure. Where will I measure all these kind of
Exactly. Where would you put your sensor, right? Yeah.
After all, I wanted to see the, let's say, the strain. So there will be, I mean, when this is expanded in this direction, the expansion is throughout.
Yes.
So I could attach a small resistive element and see its dimension change.
Yes. And in this case, if it's the same throughout, you could probably attach it anywhere you like.
Correct. In this case.
In this case, yeah.
Yes. So something like that is what done here.
Is that what you're trying to do here? So you have a solid steel structure.
Yeah.
You want to look at its extension? Is that what you?
In this case, it could be an extension or it could be a. We will see this later.
Okay. Okay.
Because strain gauge, strain, if you're measuring, you can derive various other parameters.
Okay.
Which is of practical use.
Okay.
We'll see that. For example, torque, for example.
Okay.
But the point is, here you have attached something to this structure to look at the expansion or contraction of that structure.
Right. It's on it.
It is on it.
Yeah.
Now, if that resistive element is made of this, what kind of shape? When you attach this resistive element to that big structure,
yes,
the resistive element is also undergoing the same dimension.
So you're saying this is our structure, you're attaching something to this.
So I said two things. See, the dimensional change is what we are measuring.
Yes.
Now, we are taking a case where there is a structure which carries some load and there is a dimensional change that I want to measure.
Okay, so we are interested in the dimension in that structure. Okay.
To measure that, I attach another element to it.
Okay.
Which is firmly fitted to that.
Right.
So, if that structure undergoes expansion or contraction, this element will also undergo expansion.
Because it's on it.
It is on it, yes. Right. And for both structure, what we derived is valid.
Okay, I see what you're saying.
Yeah.
Both structures could be like this.
Could be like this, right? Yeah.
Okay. Whereas if you
this equation is generalized equation for any conductive material.
But then if you have a large structure and you have a smaller structure attached to it, right, the actual change will be much larger in the or you might be able to even see it.
So there, what I will do is I will go for maybe this delta L by L.
Specifically,
so
delta L by L. Why is that? Why not the other?
So that there is also a relative change now.
Okay.
So the big structure may have, because it is lengthy,
yes,
it may have more delta L, but then it is also divided by the same L.
Yes.
So the unit change or the per unit change is the same.
Yes.
Hope we are not complicating.
No, I think that's clear. This principle applies to both the structure and
what is attached.
To it, right? So
that understanding is important.
Yeah.
Otherwise, we may think what is attached alone is going through change, or the other one alone is going through change.
Yes.
It's not like this. Both expands at same relative change.
Yeah.
Now, see, so far we were saying expansion, contraction. So that means maybe what we are more interested is this delta L by L.
Especially if you're doing something like this.
If you are doing like that.
Yes.
So I would like to, know if I have a delta L by L, what will be the delta R by R?
Okay.
Try to relate it in that fashion, if that's what I wanted to observe.
Okay.
Now, the other question is, can I somehow, for a material, when the volume is same, when you change L, the area is going to, if L is more, area will decrease and so on. This also we know.
Yes, because the diameter decreases.
Yes. So there may be a way to represent delta A by A in terms of maybe at least in terms of diameter. Because diameter of circle like this, we know it is, if the diameter is area, if diameter is D, area will be pi d square by 4.
Yes.
So if I want to represent, let's say, change in A in terms of change in D, I can say, I can take a derivative of A with respect to D. So that will be I over 2 delta A will be pi D by 2. Yes. Into delta D. Because it will be derivative of A with respect to D.
Yes. And you just take it to the other side.
Yeah, delta A by delta D. That's what we have written.
Yes.
So that will be this. So maybe delta A we could represent using delta D. We will see that.
Okay.
I wanted to have a relation in terms of delta R by delta L by L, if
Yes.
that is possible.
Yes, because if you're talking about the area, it's not very intuitive, is it?
Correct.
Right?
Correct.
Area is also a function of D.
Yeah.
So then,
It's not something that we can easily make use of.
yes, yes. But if it's D,
Yeah.
then we can kind of get an idea.
Yes.
Yeah.
How?
It's just graph.
So, although we said all this,
Uh-huh.
you may have a feeling that, see, the force that I apply, yes, I keep increasing. What will happen?
That depends on the material that you're pulling.
Yeah.
And also the material that's on it.
Yeah. So now consider that base material itself.
Even the structure itself.
Yeah, the structure itself. It could be this itself, this whole structure itself.
And you keep pulling this structure.
Let's say you are keep pulling. What will happen to that?
After a while, it might.
After a while, it will break.
It will break.
Of course, depending on the size
Yes.
and type of the material, you may have to apply much more.
Yes, if it's steel, for example, you'll have to probably apply rash force.
Correct. Correct. So what we had discussed initially is some range for which the deformation that we talked is in the elastic range.
Okay.
Means it's almost like our rubber band.
Right.
You
Pull.
pull, if it expands, you leave it, it comes back to original position.
Yes. And if you keep pulling, it will break.
It gets some point. Right. Although it's not a great example,
Yeah, but the
It's
idea behind is
it's
the
the
same,
same.
right?
It's
Yeah.
the same. Yeah. So for the metallic elements, there is some range for which the stress that you apply and then the strain that you have is in the elastic zone. Okay.
And I can say it's linear.
That's also linear.
Linear.
Right. Now, as you said, if I keep increasing, I will reach a point. From there, if I apply further, I may not be able to come back into the elastic zone.
Right.
So I make a permanent deformation.
Yes. Yes.
Right.
So it might not break,
Yeah.
but
You have deformed
in a way that you will
it's
not.
not coming back to our earlier rubber band position.
Yes.
Right. So that is this yield point.
Okay.
And if you continue apply, you cross the ultimate strength and it gets ruptured.
Now, Bobby, one thing I want to clarify is you're now still talking about the structure, right?
Yeah.
The other device or
Yeah.
thing that you showed, something was on it,
Yeah.
pasted on it.
Yeah.
Is that, I believe, is a different material.
That usually it's a different material because that we are choosing. We want, as you said in the last class, we want higher sensitivity. It should be less sensitive to environmental factors.
Right.
All this we want.
Yes.
So we will select. Also, it has to be selective. Many parameters. So we will select something that gives all these factors we love to have.
Okay.
And then attach it to the structure.
Right.
Which undergoes the. Now, as you mentioned, of course, we don't want to fail that large structure. That's why we are probably monitoring this.
Exactly.
Correct?
Exactly.
So
Right.
that also we don't want to go through the that material. Preferably, we will come to such applications. It will become more clear.
The material that's on it.
Yeah, both.
So when you look at the graph like this,
Yeah.
Do you first look at the material that's on it, or do you, because as you said, if you're going to measuring something from the structure, we don't want that structure to break, right?
Correct. So what I'm saying is, this is actually a general characteristic of a metal.
Metal while you're pulling it, for
Yes,
example.
yes. So it is valid for both.
Okay.
And when we design the resistive element, we will ensure that it elongates only in the stress that is seen by it is in this elastic zone.
Okay.
Same is valid for the other material.
Right.
Because let's say I want to make use of this to measure some mass.
Okay.
So I may not be able to make a structure to measure the mass using the resistive element alone. So I may have a structure, we will see soon.
Okay.
So I may have a structure where I will put the mass. There may be some dimension change like this. I attach, like we have shown in this previous diagram, I attach some thin resistive element like this. We will see its shape soon.
Okay.
And see its dimension change. Right?
Right.
So
And based on that, you'll be able to derive the
for
mass.
Yeah. Okay. Right.
Okay.
So the structure it is attached to and the element that you are attaching, both will be in the elastic limit.
Right.
Yes. By design.
Yes.
Now, if you overload so much, it may fail.
Right. But I mean, I
That's
guess
the time actually it goes to the it crosses the yield point and then
go to rupture stage.
Yes.
But I mean, I guess it's better to break this sensing element than the actual structure that you're measuring. I guess you can always replace it. I mean, you can replace the structure as well, but I think ideally it's probably more expensive. I don't know. I'm just
correct. Yeah. Usually, I think the examples will make it clear.
Okay.
So far what we have said is there is dimensional change. Correspondingly, there is a change in resistance. It can come from the change in length, change in area, change in the resistance.
resistivity.
Another factor what we are saying is you should be in the elastic zone of that material.
When we are making the measurements.
When we are, so suppose if you are designing it, you should design in a way that you should know, okay, for this application, this much is the stress expected. So my material stress strain characteristic is this. So it matches with that. So I go for this.
Okay.
Yeah, I think this discussion we had, delta R by R is this.
Yes. Oh, that's what you derived.
Yes. So, yeah.
Two of your friends or?
Yeah, I would like to, but Lord Kelvin, is a really great scientist.
Yes.
He has invented this in 1856.
Oh, really? You mean this means this kind of idea?
This kind of idea, saying that, there is dimension change like this, you can make use of this to measure some physical parameters.
Okay.
And that was primarily for conductor. Let's say, kind of material. It could be even copper or nichrome and so on. But then later, after, probably 100 years, right? Smith, he has found, okay, you can also use silicon and germanium or semiconductor material for the same application. He found that it has got much more sensitivity.
Okay.
Sensitivity.
So, sensitivity.
So that means delta R by R.
The response.
For a given delta L by L is large for semiconductor. That's what he identified.
Compared to the conductor.
Yeah. But I see that conductors, metallic elements are still used for this application. By the way, here the name is also there. When you have, when you make use of this idea to measure the strain, it's called as strain gauge.
You're missing it. Yeah.
So I've seen both.
Really? This is actually the first time I'm saying it like this.
So
maybe the American and British way of
GAUG. Correct? Yeah. Because I've seen the other spelling also.
Yeah.
So usually when I teach, we will write only SG. So safe.
Yeah. Anyway, that's not so important. It's what's important.
No, it's also important. Some in some cases people may be very careful.
I guess so. Yeah. They were, what is this? It's the same thing as a strain gauge. Yeah.
See, some teachers may be very strict. But I've seen both spellings. So earlier we were trying to do some relation between, we wanted to replace this delta A by A, preferably with the delta L by L.
Yes.
And then I was trying something, I got this expression in the previous slide, one slide before.
Yes. You got the derivative.
Yeah. We said delta A is this.
Yes.
And then we were thinking what to do next.
Yes.
Right?
Now you have it in terms of D.
Yeah.
But, okay.
We would like to get actually in terms of L itself.
Right. Okay.
And of course, from here, if we divide with area, both sides, delta A by A, you will get 2 times delta D by D.
Yes.
Right? So, of course, this I can replace and write this.
Yes.
Yeah, partially happy. Everything else is fine. But then there is actually for the material, there is something called Poisson's ratio, which is the ratio between delta L by L and delta D by D.
Oh.
Yeah.
So there is a...
Yeah, that's a known relationship. Right? So delta D by D by delta L by L is lateral strain by longitudinal strain. Okay.
It's called Poisson's ratio.
Yeah. So for a material in the elastic range, this is known. Okay. There is a relationship like this. Because you are, as we logically, when we said, when you are expanding, there is a reduction in the area. And if you are contracting, of course, it's diameter will increase.
Yes. And people have done experiments to see.
Yes.
To show that there's...
Yeah. So you have this nice symbol which represents this. Right. So that means this, we have written in this form of this. Now, delta D by D, I can replace in terms of delta L by L into Poisson's ratio.
Yes.
So that's what it is done here.
So now you got rid of T.
Yes. Now we are getting closer to delta L by L. Right?
But you still have your Poissons.
Rho by rho.
I
I think that is material property. You may not be able to play with that.
Not really a dimensional property.
Yes. We may not be able to represent that in terms of delta L by L. Okay. So now I can bring delta L by L to this side. So I get delta change in R or relative change in R divided by relative change in length, which is the strain. Right? Is 1 plus 2 times Poisson's ratio plus delta rho by delta L by L.
So this is the resistance change?
Yeah.
Per
unit strain.
Per unit strain.
Correct. Because you have delta R by R divided by delta L by L.
Okay. In terms of Poisson's ratio?
Yeah.
And the resistivity.
So the Poisson's ratio is known for the material.
Yes.
So if you know that information, you can actually calculate what is the factor of change in resistance that you will have if it undergoes this much strain. Okay. So that factor you may want to call it as something. I think it's called as it's a strain gauge.
Then I would say it's called
gauge factor. Yeah. So that's called as gauge factor. So I've seen for metallic strain gauges. The conductive we have mentioned in the previous slide.
It's normal conductors.
Yes. Yeah. So if you use metallic strain gauges, the gauge factor is maximum
2%.
Yeah. It will not be.
Sorry.
So
2 is the factor.
Yeah. 2 or less. That's what we have seen. Right. Now, one thing. See, this is the change in the or relative change in resistivity with respect to strain, delta L by L.
Yes.
So the resistivity of the material is changing due to strain.
Yes.
So
is there a factor for that as well?
It has got some other name. So it's a property of the material. Usually we see this more in semiconductor material. So it's called piezo resistance coefficient.
Piezo resistance coefficient.
Yeah.
Okay.
So it's again, resistivity of the material is changed. There is a dimensional change.
So even for a normal conductor, if you look at the data sheet,
Yeah.
you will see this piezo.
It will be there, but
resistive coefficient.
for metallic objects, this amount will be very low.
Okay.
And mostly it comes from 1 plus 2 times Poisson ratio.
Okay.
Now, if you go for semiconductor material, this 1 plus 2 times Poisson ratio may not dominate. On the other hand, the piezo resistance coefficient will be quite high.
Now you mentioned normal conductors have a gauge factor about 2.
Yeah. So 2, it's a more precise here, 1.8 to 2.
6.
Yeah.
Oh, so the semiconductor type.
It's
It's much higher.
100, 150.
Yeah. Up to 10 times higher.
Yes, it's actually very large.
Okay, so that's a significant difference.
It's a significant difference.
So then, why would someone use a normal conductor compared to a semiconductor? Is it to do
People are
with,
still mad. I don't know.
or is it to do with cost
Not really.
or fabrication complexity?
Could be, but not really the cost.
Uh-huh.
I still see metallic strain gauges widely used. There is some reason for that.
Okay.
Because if you look at the resistance of the element with respect to temperature, which is also high for semiconductor materials.
This is true.
Yes, correct?
Yes.
But for metals, not much.
So that could be a factor there.
So earlier you were discussing about selectivity.
Yes. Now if it's
I don't want change in output due to change in temperature.
yeah, so you're saying if somehow this material elongates due to temperature,
Or it need not elongate. Let's say there is no strain,
there's no strain.
but temperature changed.
Uh-huh.
Change in resistance. Oh, we say, lot of strain. This structure is under this.
That's true. That's true. And it was a thin structure too.
Yeah.
So if it's maybe really hot,
Correct.
it might deform in some way.
Correct.
I mean, that's an indirect way.
Correct.
You're saying it a direct way.
Yes.
Resistance and temperature.
Yeah.
So that could be a problem.
Yes. So it is also sensitive to other parameters like temperature. So it has got that issue.
Right. I assume there's probably a way to compensate for that.
Could be if to some extent. But other factor is, see, this metallic strain gauge is metal. It's you can choose the material, and you can choose maybe materials that are somewhat inert. Even chemicals may not refer much to that.
Right.
So there are certain benefits for metallic strain gauges, and they are still in use.
Okay.
I was also looking at typical values of this strain gauges.
Okay.
It comes like 120 ohm, 350 ohm, 1000 ohm, etc.
Okay. So quite
Yeah, not very large.
not very large. Yeah.
So you may have to send some current or form some way to. There may be some circuit required to measure from this precisely.
Right. So that means if your resistance is increasing, your current is somehow decreasing.
It depends on how you are doing.
Uh-huh.
Yeah. So correct. If you are applying a voltage across it and measuring the current,
Yes.
it is like that. But another factor is when you are sending current through that continuously, there may be some problems.
You mean like heating?
Yes. So environmental temperature need not change.
Yeah.
You are self-heating it.
Yes.
So that may also result in output. For example, if it is sensitive to temperature.
Somehow modifies the
Somehow modifies.
the
See, last day you were showing the drift. Output keep on increasing with respect to temperature or decreasing and so on.
yes.
So it can happen. You turn on, there is some amount of current going, there is some self-heating. We change the resistance increases. Or you see that, okay, there is strain.
The stress. But it's not.
Yeah, so one can get fooled.
Yes.
If you don't choose the material correctly, if you don't correct for it, and so on.
Yes. But these kind of resistances, I guess, are not too small. If you had like 1 or 2 ohms, maybe it will heat up faster, I think. I mean, again, depends on the current you set through.
Yes. What we can do is we can choose materials with low temperature coefficient and still has good resistance or resistivity value.
Right.
So people use material like nichrome, which is made using nickel and I think chromium. Yeah. So this is some theory behind, how to make use of dimensional change in the resistive element to capture some information.
Yes. From some application.
Yes. And that information can be strained. And for that structure, if you know the stress strain characteristic, from the strain you can also get the stress.
Because it's a linear relation.
Yes.